This week we're learning about double integrals, both over general regions and over rectangular regions. This is an example of how we introduce double integrals over a regular region. I take the graph of a two-variable function, my x and y coordinates. The left represents the domain of that two-variable function, and I go ahead and graph it in a three-dimensional space like over here. I think of the double integral as telling me the volume trapped within this box down here in the xy plane and the surface above. We will estimate the volume of that region by taking the region inside our domain, subdividing it into a few pieces like these four rectangles. So we take the big rectangle and subdivide it into these four rectangles in a systematic way. Then we can estimate the volume of the region by taking the height of the rectangle as being just the same thing as a point on the surface for at least one of the points inside the rectangles. This software is going to assume that it's always going to be the bottom left corner point. We find the volume for each of those rectangular prisms or rectangular boxes and add them all up. The sum total gives us the estimate of the region of the volume. If you remember from Calculus 1 when we did this trick for single variable functions, we got a better estimate by increasing our partitions. Partitions work slightly differently because you're partitioning both the x and the y with that number of partitions, or that index of, say, 3. And since you're doing both x and y inside the domain, the effect is squaring. With each new partition, your sum becomes a better and a better approximation of the volume. If you let n get infinitely large, you might guess that these sums will converge towards the actual volume. If it does, we say the limit exists, the limit of the double integral exists, and that is the volume of the region. In this assignment, you're asked to find the estimated volume of your chosen function, something different than the one I have graphed here. So I'm going to explain how to use this applet to be able to do that. First of all, when you do the estimated volume, you could just do it with a total of 4 boxes, so a partition of 2. Secondly, when you want to put another function, you want to put a function in here that you can actually just see inside this expression. It doesn't have to be overly complicated, though you can make it a more complicated function if you want. But just to get the right graph, if I say wanted to put in x squared plus y squared plus 1, I click on this box and I use delete and my keyboard to fill in everything else, press enter, and I see this graph. And I maybe think, well, I can't quite place it in the graph exactly so I can see it. So maybe I want to change something else. I can either shrink my window by shrinking these, so the box, so that everything fits into the window that I have here. Or if I don't want to do that, I could just change my graph a little bit and say, well, the problem is my x variables are just too large, so it shoots up too fast. And my same thing with my y variable. So I just multiply it by something that shrinks it, like 0.5. Now I can see that when I look at the pictures that I'll eventually post or take screenshots of, I can clearly see that that rectangle has a corner on the surface. On my paper, I would calculate the volume of this by using the function that I just entered in here, plugging in the coordinates of the points that I want to plug in. So I get to move these around to make sure the coordinates of the points are things I can find easily with a graph. I can cycle through the next rectangular cube to find the volume of by just moving the slider over. So this will be the second one, and this will be the third one, and this will be the fourth one. I make sure to get a screenshot for each of them and post each of the 4 screenshots. And then my summed calculation of their of the volume of the approximation right over here. Just post those things and you're done.